Hello everyone. My name is Urvi and I'm a software engineer at Microsoft. I welcome you to this part 4 of 5-part series by Scalar where we're covering linked list data structure end to end. So in this lecture, we're going to see another type of linked list. What we have seen so far is a singly linked list, and why it is called a singly linked list, because every node in a singly linked list has one link where it is pointing to its next node in the list. In doubly linked list, as the name suggests, every node will not have one but two links. One link will be to the next node and one link would be to the previous node in my list. Alright, and that is why it is called a doubly linked list. Now, what are the advantages of having two links for every node? Now, you see, you can imagine a doubly linked list to look like something like this. For example, if you have three nodes, here each node would be pointing to its next node and also its previous node. So you see double links for every node, and this is an example of a doubly linked list. Here the first node's previous would be pointing to null, just like the last node's next would be pointing to null. Okay, so again, but we will have the first node be pointed to by head so that we know where our linked list, doubly linked list, is exactly starting. Okay, so this is how you can imagine a doubly linked list. Now, what are the advantages of having a doubly linked list? So in a doubly linked list, we can traverse in both directions. Right? In a singly linked list, what was happening so far? We were only able to move in the forward direction because every node only had access or link to the next node in the list. Okay, so it was not possible for me to move backward. But here, since every node also has a link to its previous node in the list, we can also move in the backward direction. We can also traverse our linked list in the backward direction. Okay, so this is one of the advantages that we have. Another advantage is the insertion and deletion becomes easier. Why? Again, because we have links to the previous node and we have links to the next node. So insertion and deletion would become easier here since we're able to move in both direction, forward and backward, from any given node. But considering these advantages, there is also a disadvantage. There is also a disadvantage, that is the extra space occupied by the second link. Okay, in doubly linked list we have two links, so there would be some extra space that is being used by the second link. So that is one of the disadvantages when we are using doubly linked list over singly linked lists. Okay, but considering this, we will find a few examples where we need to traverse a linked list in both directions, and that's when a doubly linked list would come in handy and save us. So let's move forward and see how would we define a node, a single node in a doubly linked list. What are the things that might change here from the singly linked list? Okay, let's first revise what was happening in singly linked list. So in a singly linked list, every node had two parts. First was the data part or the value part, which is storing some value for us, and the other part was the next part, which was basically a pointer to the next node in the list. Now in doubly linked list, we have a third part to this node, which is called previous, and this is the link to the previous node in my list. Alright, so this basically means that in doubly linked list, every node will have 3 parts. Okay, so these nodes will have some values. The previous of the first node, okay, the first node, which let's call it the head node where our linked list is starting, the previous of this head node will be null, and the next of this node will be pointing to the next node in my list. Again, in the second node, the previous would be pointing to the first node, and the next would be pointing to the third node. For the third node, the previous would be pointing to second node, and the next would be pointing to null. Okay, so this basically means that our list ends here. So whenever we see a node which has for which the next pointer points to null, that means my list is ending there. That means that is the last node of my list. And although the first node we can check from the head, head pointer will always have on the first node, but also another another unique thing about the first node will be the previous pointer of the first node will be pointing to null. So this is how our node definition would look like in a doubly linked list. Let's try to implement this, and we'll also see the traversal side by side. Okay, so we sort of know how to traverse a singly linked list the same way we'll be implementing here in doubly linked list. But the difference would be here we will be able to do not just the forward traversal but also the backward traversal. So first of all, let's create class node here for our doubly linked list. Okay, we're calling it the same. If you want, you can call it another node, but still, like when you talk about singly linked list, doubly linked list, or any other type of linked list, the node is a node, just the definition of it will change. Okay, so in this case, in the definition, first of all, we will have some value that we'll be storing in our node, and then we will have 2 pointers. These pointers will be of type node star because they'll point to another node in my list. So first one node star next, and another one node star previous. Okay, let's also create a constructor here. So if I'm passing any value d, so it should put that value in my variable value, and next and previous we'll make it null initially. Okay, so this is what my node definition looks like in a doubly linked list, for a doubly linked list. Now let's try to create a doubly linked list using this node. Okay, so I'll create node star n1 is equal to new node with some value 1, and node star n2 is equal to new node with some value 2. Okay, and now here if I make node 1's next point to node 2 and node 2's previous point to node 1. So we've connected my 2 nodes here in doubly linked list. Also let's make this public so it's accessible. Alright, so n1's next is n2 and n2's previous is n1. Okay, and let's also create a pointer head which will be at n1. So here I've created a doubly linked list which has 2 nodes, n1 and n2, and if you want to print this doubly linked list, let's write a traversal function for that. Okay, first of all we will write traversal for forward. Okay, let's call it forward traversal, where we'll be passing the head of my linked list, and To traverse my linked list, I'll create a temp pointer, make it point to head. Now we'll keep moving this temp pointer ahead till temp reaches the last node. Or let's say till temp reaches null, we'll keep moving temp forward. Okay, and we will also print the value of temp. Alright, so what are we doing here? We've created a temporary pointer temp, and we're using that to traverse our entire linked list. Right? In this linked list, we are traversing till temp reaches null, because when we start traversing our linked list, at some point when we move to the next, when it is at the last node and it will move to the next of last node, it will reach null, and that's when this loop will break. Till that time, we will keep printing the value of temp, and we will keep moving our temp pointer ahead. Okay, at the last I'm just printing null so that we know our linked list has ended here. And let's call this function forward traversal for head. Okay, so this is the linked list that is being printed here. I haven't added arrows here. Okay, if you want, we can add arrows, but keep in mind that these arrows are bidirectional, right? Both ways these arrows would be going from 1 to 2 and from 2 to 1, right? But not for null, obviously. From 2 to null, there only be one link, no link from null to 2, obviously. Okay, so I don't want you all to get confused here, so we'll just keep it at that. Okay, this is my doubly linked list. And so another thing that I want to mention here is, here we are only making use of the head pointer. In some cases, we can also, use a tail pointer which will be pointing to the last node of my list. And where would that be beneficial to us? When we want to access the last node of my list, because right now if I only have the head, I'll actually have to use a pointer and go till the last node. But if I have tail pointer, then I already know what is the last node and I can traverse back from it. Okay, so here I'm not taking the tail pointer, but you can do that if you feel like in any particular question, having a tail pointer to the last node of the doubly linked list can decrease your time complexity or can help you greatly. Okay, so coming back here, let's write a function for backward traversal as well. Node star head, node star, again we'll have to have a pointer, temp pointer, that will be starting from head. So for backward traversal, first of all we'll need access to the last node, right? So for that, let's move our temp pointer till the last node, till temp of next doesn't become null. And when will next of temp become null? When will next pointer of any particular node become null? When we are at the last node, right? So till that happen, we'll keep moving our temp pointer ahead. Now we are at the last node, so we can start traversing back. Again, we'll keep a condition while temp becomes null, because it will become null as well when we start traversing backwards. How? Let us see. If I keep doing temp is equal to temp previous, so at some point when it will reach the first node in my doubly linked list and it will go to previous of that, it will reach null. right? So in this case, we'll keep while temp, and we'll also print the value of temp. And in the end, let's just print null, right? Because even if we are traversing backwards, even then at some point we will encounter null, right? Because the previous of the first node points to null. So let's call the backward traversal function here. So you can see this is the forward traversal of our linked list, doubly linked list, and this is the backward traversal that we have here. Alright, so this is how we can traverse a doubly linked list. Let's move forward and discuss now how insertion and deletion operations would become different when we're talking about doubly linked list. So starting with insertion, where we are talking about adding a node or inserting a node at the start of a doubly linked list. So let's assume we have a doubly linked list, something like this, and we want to insert a new node at the beginning. So first of all, we do have access to the first node through the head pointer, and our first step here while inserting would be creating the new node, right? Let's call this the new node. This is the new node that we have created. Now to insert it at the beginning, what I'll have to do, first of all, I'll have to make the new node's next point to my head, my head's previous point to my new node. Okay, these are two steps, and the third step would be to move my head pointer to my new node. Okay, so three things that I need to do to add a node at the start of my doubly linked list, and the time complexity here would be O of 1, constant time complexity, because we're not traversing our linked list. So let's write the code for this. Void insert at start, where we are passing our doubly linked list by reference, and the first thing, also in the parameter we miss the value, so we'll also pass the value of the new node that we want to insert. Alright, so first of all, let's create a new node. Node star new node is equal to new node with the given value. And once we have the new node, then what we want to do is, in the new nodes next, we want to add the current head node. In the heads previous, we want to add our new node. Okay, the new node's previous would be by default null, so we'll keep it at that. And finally, we'll move head to, not null, sorry, to new node. Okay, so now our head is at our new node that we've inserted. Let's test this. Insert at start, passing the head and passing some value 9, and let's check the forward traversal. So you can see 9 got inserted at the beginning of my doubly linked list. Next, let's discuss how to add a node at the end of my linked list. Okay, so considering this is our linked list, again our first step here would be to create the new node with the new value that is given to us. Let's call this new node. And here we would have access to the first node of my linked list through the head pointer, but I'll have to get access to the last node, because after the last node I need to insert the new node. So I can create a pointer temp and use it to traverse my doubly linked list till I reach the last node. I know I will reach the last node when its next becomes null. So after I have reached to the last node, what I'll need to do is simply in the last node's next I'll put the new node. In the new node's previous I'll put the last node, which is pointed to by temp pointer, and new node's next is already null by default, so we don't need to change that, and that is how we'll be able to add a node at the end. Again, here the time complexity would be O of n because we need to traverse to find the last node, but in case we had a tail pointer here at the last node, the time complexity would have been simply been O of 1 constant time complexity. Okay, so void insert at end node star head and the value that we need to insert. Okay, now first of all let's create the new node. Okay, node star new node is equal to new node v, and to traverse to the last node we'll create a temp pointer starting at head while temp next. Okay, or we can also call it last node, since we want to go to the last node using this pointer. So till the next of last node doesn't become null, we'll keep moving this pointer forward, and once we have reached to the last node, then in the last node's next I will put the new node. In the new node's previous I'll put the last node, and that will insert the new node for me at the end. Also, let's consider an edge case. In case my head is equal to null, meaning my doubly linked list is empty, there is no node in my linked list yet. In that case, this line will throw an error when we try to access the next of null. Let's also consider edge cases here while inserting. Okay, in both of these cases, these can throw an error if my linked list is empty. Okay, how? So let's see if my head here is null. Okay, there's no node in my linked list yet. So when I try to access previous of head, it will throw me an error, right? So let's just say if my head is equal to null, meaning my linked list is empty, in that case my new node will become my head, and I can return from here. I don't need to do these steps. Or else another way to deal with this is if my head is not equal to null. Okay, if my head is not equal to null, then I'll perform these steps. If my head is not equal to null, meaning I have at least one element in my linked list, in that case we'll follow this approach. In the new nodes next, I will put my head, and in the head's previous I'll put the new node. Okay, and if my head is null, then all I need to do is just make my head pointer point to my new node. Okay, similarly here also this will fail when we try to access next of head if my head is null. So let's just say if my head is null, if my head is null, then we can just make head point to my new node and return. Okay, I don't need to do anything rest of this if my linked list is empty and I'm trying to insert at end. Okay, moving forward to inserting a node in the middle of my doubly linked list. Okay, so let's assume we are given some value k which tells us the position at which we want to insert my new node. Okay, and let's say k's value is 3 or let's say 2. So first of all, for adding a node here, I'll have to create a new node. So I created a new node. Okay, now to add a node at k position, I'll first have to go till k minus 1 position. Okay, so this is my head and this is also my k minus 1th node. So I'll traverse till my k minus 1 node, and of course we'll keep a different condition if k's value is 1. In that case we are just trying to insert at the beginning, so we'll call that function. But for any value of k which is more than 1, we'll first go till k minus 1th node, and then for that node and for its next node, for the kth node, we'll have to change the links, right? What all will need to be changed? First of all, let's call this as temp. Okay, let's call this as temp node, and this is temp's next, right? This node is temp's next. So temp's next previous is right now pointing to temp. Okay, we'll make this point to, we will remove this and we'll make the temp next previous point to my new node, and we'll make our temp's next point to my new node, and then we'll change the links for new node as well. We'll make our new node's next point to temp next. So we'll do this, we'll not change this link. Okay, we'll first of all add links between temp next and my new node. So temp next previous should point to new node and new node's next should point to temp next. After I've done these changes, then I'll say temp next make it point to new node and new node's previous make it point to temp. Alright, so I've added all of the links now. Okay, I have all of the links between my k minus 1th node and new node, both my next and previous, and I also have all the links between my new node and k plus 1th node. Okay, one other edge case could be when k's value is equal to n, the number of nodes. So for example, if we have 4 nodes, okay, after including the new node, and I want to insert the node at 4th position, basically at the end of my list. Again, if you follow the same approach, I'll move first of all to the k minus 1th node, which will be this, my last node. Okay, this will be my k minus 1th node, and if I want to add a new one, first of all this next would be pointing to null. Okay, so this will be my temp next, and when I try to access temp next previous, it would give me error. Okay, so I'll need to keep a check. If my temp next is not null, only then I'll change its previous link and point it to my new node. Okay, else what I'll do is just make my new node's next point to null, and I'll change the links between these two nodes. Alright, so in doubly linked list, although the insertion, deletion, traversal, backward, it becomes easier, but a little bit of complexity increases because we need to take care of whenever we're trying to access, the next of previous or previous of next node, we need to check if it is null or not, okay? Because if it is null and we do not add an edge case or a check for that, it will throw an error and break our code, okay? And the time complexity here would be O of n depending on the k value. So let's just say O of k. So let's come to the implementation now. Void insert at middle, where we have our node star head, we have the value to be inserted and we have the k position at which we want to insert the new value, okay? So first of all, let's check if k is equal to 1. If k is equal to 1, that means we just want to insert at the beginning. So let's just call this function insert at start for the new value. Else, if k is more than 1, in that case what we'll do is first of all traverse to the k minus 1th node. So for that, let's create a pointer temp which is starting at head, and I'll create a for loop where this loop will traverse till k minus 1 and temp will keep moving forward till I reach my k minus 1th node. After I do reach my k minus 1th node, then I need to make changes between, first of all, the next node, which would be the current kth node, and the new node, okay? So let's create the new node. Node star new node is equal to new node with the value v, and we'll say temps if temp next is not equal to null. In that case, make temps next previous point to my new node. We'll make our new node's next point to temp next, okay? Now we've made changes between the new node and the previously kth node. Now we will make changes between the k minus 1th node and the new node. So we'll say temps next, make it point to new node, and new node's previous, make it point to temp. So this is our code for inserting in the middle. Let's test this. Insert at middle head, and let's insert the value 3 at position 2. Okay, we didn't call the forward traversal. So this was our linked list, and we inserted the value 3 at position 2. If I insert it at position 3, I can see at position 3. I can also insert at position 4. Okay, so 3 is inserted now in the end, and I can also test for insertion at position 1. Okay, this is inserting it 2 times because we are not returning here. Alright, so make sure to return from here in the if condition if you are calling this function to insert the element at the start. Okay, so it's always good to test your code with all the different values so that you can test if you left out something. Okay, cool. So moving forward to deletion now. We've covered insertion. let's move forward to deletion. First of all, deleting a node from the start of my linked list. So for deletion, again we'll have to take care of both of the links. If you want to delete this head node, okay, I'll move my head pointer to the next node. Okay, first of all, let's make this pointer node that needs to be deleted pointed to by a pointer. I can make a temp pointer, delete node, whatever, some pointer pointing to the node that I have to delete. Then I'll move forward my head to the new head after I delete my first node, and I'll make the previous of my head point to null. Okay, so you can understand it like this. I'll change this and make its previous point to null. Okay, because this is the first, it will be the first node now, so I'll have to make its previous should be pointing to null. Okay, and then I can get rid of my first node. So let's look at the implementation. Delete at start node star head. So let's say temp is pointing to the head node that needs to be deleted. We'll move head to heads next, and then I can say heads previous should be pointing to null. And finally, I can free up the temp node. Okay, again this code will throw an error if I only have one node in my doubly linked list. So I can add a check if my head is null or my heads next is null. Okay, in case my linked list is empty, or actually let's just consider the case where it has one node. Okay, let's assume that there will be at least one node if I'm trying to delete something. But if there's only one node when I'm trying to delete at the start, in that case I can just do free head and return. Okay, in that case I don't have to do all of this. So delete at start forward traversal, let's check. Okay, we need to make this condition as if heads next is equal to null and not if it's not equal to null. Okay, so in this case 3 got deleted from the start, and now we have this as our remaining doubly linked list. Okay, so I hope you caught that. We just missed comparing head next with equal to null here. Okay, if we just put it head next, then what it was doing was it was checking that okay, this is not null, so I'll just free up the head and then my linked list was gone, right? If you free up the head, there's no linked list because you lose where your linked list is actually starting. Okay, so good catch here. Always take care of the condition that you add in if, and the time complexity here would be O of 1. Moving forward, deletion from the end. Here, while deleting from the end, we'll have to traverse to the end of the list. So we'll take a pointer temp, use it to traverse to the last node of my doubly linked list. Okay, and let's make temps previous. Let's say this will be my last node after deletion. So I'll make the last nodes next I'll remove its next and make it point to null, because the last node's next should be pointing to null, and then I can free up my temp node. So void delete at end node star head. So first of all, a pointer to reach the last node starting from head, while temp next is not equal to null. Till then we'll keep moving our temp pointer forward. Okay, now our temp is at the last node. This is the node that needs to be deleted. And what will be the new last node after deletion? That will be temp's previous. So I'll make the new last node's next point to null, and then I can free up temp. Okay, and again we can add a condition, the same condition here. If we only have a single node in my doubly linked list, then I can just free that up and return from there. I don't have to do any of the else things. So delete at end head, and let's check the forward traversal. So this was my linked list, and after deleting from the end, 2 is removed. Okay. Finally, let's see how to delete a node from the middle. So if I have a linked list, doubly linked list, which looks like this, and this is the node, the k value that is given to me. What do? First of all, let's traverse to the k minus 1th node. Okay, and let's call this temp, just like while inserting. Same way we'll traverse to the k minus 1th node. We'll make temp's next get pointed to by delete node, meaning this is the node that needs to be deleted. Now we'll have to change the link between this temp node and this node, which is delete nodes next. So this delete nodes next, before deleting it, we can make these changes using delete node pointer. We can say temp's next, make it point. We can edit this and say temp's next should point to the delete nodes next, and delete nodes next previous should point to my temp node. Okay, and once I have added these two links, then I can get rid of my delete node. Okay, and the time complexity here would be of k, depending on what is the k value given to us. So void delete at middle node star head, and we'll be given some k value which will tell us where exactly we need to delete our node. So let's check. First of all, traverse to k minus 1th node. So we'll start a traversal from head, and let's create a for loop starting from I is equal to 1 till k minus 1 I plus plus. I'll keep moving my temp pointer ahead. Now my temp pointer is at kth node. What will be my delete node? The node that needs to be deleted, that is temp's next, right? That's the kth node that needs to be deleted by me. Next we'll say my temp next should be pointing to my delete nodes next, and if my delete nodes next is not null, then my delete nodes next previous should point to my temp, okay, because it could be that the k value is equal to the last node. Basically we're trying to delete the last node of my linked list. In that case, delete nodes next would be null, so we won't be able to access its previous, so we've added an if check here. Okay, so if it's not null, only then we'll make the delete nodes next previous point to temp. Okay, so now we've added both the links between temp and delete nodes next. Now we are safe to remove our delete node. Okay, and again we can add a condition here. If k is equal to 1, then we can just say delete at start and return. So let's call this delete at middle function, and let's delete at second position, forward traversal for my head. So this was my linked list 3912, and here I've deleted the element at position 2, so 9 got deleted. I can try at position 3, so 1 should get deleted. At position 4, 2 should get deleted, right? And position 1, 3 should get deleted. Okay, so it's working for all of the values. Cool. So we've seen here how insertion and deletion happens and how it is different from single linked list. So not much difference. The the way of traversal and changing the links remains the same. Just you have an extra link to take care of whenever you're inserting a new node or you're removing an existing node. Okay, so let's try and now solve some questions on doubly linked list so that this concept becomes even more clear and you become even more comfortable with this topic. So the first question is reversing a doubly linked list. So we've already done this for singly linked list, so approach would almost remain the same here, just the implementation would change a little. So let's imagine first we have 3 nodes, 1, 2, 3, okay, and these are the nodes that we need to reverse. So starting here, first of all you need to remember that the first node's previous would be pointing to null and the last node's next would be pointing to null, right? Now if you just imagine for the first node, okay, we need to reverse its links. How? Such that right now what is happening for this is its previous is pointing to null and its next is pointing to 2. We want to reverse this. We want one's next to point to null because it will become the last node in my reverse doubly linked list, and I want its previous to point to the current next node, which is 2 here, right? So let's start with the approach that we saw in singly linked list. Singly linked list we were taking 3 pointers to keep track. Here let's see if we do require in fact 3 pointers, or we would be able to solve this using less number of pointers. Okay, so first of all, with my first node, which is my head node, I'll keep a pointer current. Okay, now for the current pointer, I just told you what I need to do. I want to make its previous point to its next and its next point to its previous, right? So now first of all, if we change its next node and make it point to previous. So let's say we remove this link and we make one's next point to its previous, which is null. So I'll lose access to the rest of my linked list in that case. So I need at least 2 pointers here. Okay, so let's start with 2 pointers. Let's start with previous pointer and current pointer. Okay, previous would be pointing to the previous of my current. Now let's see if these 2 pointers would be enough for me to do the reversal. What I can do first is I can change the previous link, and I can say remove this link, currents previous, and make the previous point to 2. Okay, and how do I access 2? 2 is currents next, so make currents previous point to currents next. Okay, I did that. Then I need to change the next link, so I remove this link and I say the currents next should point to previous. The currents next should point to previous, which was being pointed to by null. Okay, let me call this previous pointer and current pointer so that you don't get confused between the previous pointer that we have in the node and the pointer that we have here for traversal. Okay, so current pointer and previous pointer. So I made current pointers next. First of all, I made current pointers previous point to current pointers next, and now I said current pointers next should point to my previous pointer, which was null. Okay, so I inversed the links for my current pointers. Now I need to move to the next node. So what I do is I will move my current pointer to its previous. I'll move the current pointer to its previous, and I'll move the previous pointer to current pointer's previous, which is this. Right? 2's previous is 1 and its next is 3. Alright, so now we inverse the links for 2. What we do first is change its previous link. So I'll say make current pointers previous point to current pointers next, which is 3, and make current pointers next point to current to the previous pointer, which is 1. Okay, and after doing this, again we'll shift the pointers. We'll say move the current pointer to its previous and previous pointer to current pointer's previous. Again, the same thing will repeat. We'll first of all change current pointer's previous link, remove this and make the previous point to its next, which is null, and make its next point to previous pointer. And once I've done that, then I move the links again. I say move the current pointer to current pointer's previous. So current pointer is at null, and now when my current pointer reaches null, I know that my entire linked list has been traversed, so I stop here. Now what will be the new head? The new head would be this node 3, and how do I access that? If you see, before I moved the nodes forward, okay, this was my case where previous pointer was at 2 and current pointer was at 3. So when I move my current pointer here and I realize, okay, now my linked list has empty, then I can say my head pointer would be add previous pointers previous. Okay, the previous node of my previous pointer here is my new head node for my reversed linked list. Okay, so now you can see head is at 3, 3's next is 2, 2's next is 1, and 1's next is null. So we have reversed our linked list. Let's see this in code. Void reverse doubly linked list, where we are passing the head of my linked list. And for pointers, first let's create a current pointer that will be starting at head, and another pointer I'll create called previous pointer that will be keeping track of the node before my current pointer. So while my current pointer is not null, what I'll do is first of all bring my previous pointer to current pointer's previous node. Then I can change my current pointer's previous to point to current pointer's next node. and then change my current pointer's next node to point it to my previous pointer, okay, where its previous node was. And finally, once I have done this, I've reversed the links, then I move my pointers ahead. So I'll say move my current pointer to current pointer's previous. Okay, I can create another pointer, next pointer here as well, just like we had 3 pointers in Doubly Linked list, but as you can see, there is no need for that. For just 2 pointers, current pointer and previous pointer, we can reverse our linked list, because here like every node has already, you know, keeping track of its previous node and next node, so we don't need a third pointer here to reverse the list. And finally, my head would be at my previous pointer's previous node at the end when my current pointer reaches null. So let's test this out. I've created a doubly linked list here with 5 elements, okay, and let's first try to print this. Okay, so we'll do a forward traversal and let's also do a backward traversal. Okay, and basically the backward traversal and the reverse of my linked list should match, right? So I'll call the reverse doubly linked list function here, passing my head,